explain in basic terms how your technology works? What are the building blocks of cryogenic cooling, and can you describe the basics? And maybe we can start with magnetic refrigeration physics.
Yes, I'm happy to do so. So perhaps to begin with, magnetic cooling is known since many decades. Actually, it was well known long before helium-3 based dilution cooling became available, also commercially available. And magnetic cooling was used to explore helium-3, which then became the predominant cooling technology in the sub-Kelvin research space. So how does it work? And perhaps why has it been used for niche applications for quite some time? So how is it set up first? So it is, as we have mentioned a couple of times, magnetic cooling is based on what is called the magnetocaloric effect. And that means that in magnetic cooling, we're using solids, no longer liquids, but solids that do not order magnetically even at the lowest attainable temperatures. So they are paramagnets, as in physics, we call those materials paramagnets. And that is quite special because most materials actually turn magnetic, so they order magnetically if you only cool them down low enough. But those materials don't. And that is interesting because what you can now do is you can polarize them by switching on a magnet. So what you do is you take those materials, those magnetocaloric paramagnetic materials, and you apply a magnetic field to them. And what then happens is that you can polarize the magnetic moments in those materials, so they eventually point all into one direction. You enforce a direction by the external magnetic field, and this creates, this first step, the heat of magnetization. So what happens is that these materials actually warm up first. So while turning on the magnetic field and applying this magnetic field to the magnetocaloric medium, the magnetocaloric medium warms up, and you have to then release that heat of magnetization to a pre-cooling unit. In nowadays commercial applications, that is typically a closed cycle cryocooler, like a Gifford McMahon cryocooler or a pulse tube cryocooler. And then the magic happens, so to speak. What you can then do is you can, of course, turn off the magnetic field again. So if you switch off the magnetic field, that means you're demagnetizing the magnetocaloric material. You actually allow the magnetic moments to randomize again, right? So they are no longer forced into a unique direction, and they, as it's a paramagnet, they want to again point into all directions. So the magnetic moments want to take their random order again, and to do that, so they take the heat from the environment, and that actually is the cooling stroke. So by that, the temperature of the medium drops, and you can then exploit that by simply connecting your magnetocaloric medium to anything that you want to cool down, right? So by establishing a mechanical rigid connection between your cooling medium and, say, your quantum setup, during the demagnetization process, you will cool your quantum setup. So that is the underlying principle of magnetocaloric refrigeration. Now, of course, there's a catch. If you think that through, cooling happens only upon demagnetization. That is why this is called demagnetization cooling. But it also means that the cooling stops once there's no longer any magnetic field left that you can remove, right? And of course, that will happen at some point. You cannot lower the magnetic field forever. At some point, typically after some minutes or hours, depending on your heat load and your specific setup, you will arrive at the point where the magnetic field is just zero. And that means that the cooling will also stop. And then inevitably, your whole setup will warm up again, right? And that is the traditional limitation of demagnetization cooling, or how it's actually called adiabatic demagnetization refrigeration. It is well known as a one-shot or single-shot cooling technology, which can provide very, very low millikelvin temperatures, but in the conventional implementation, not forever, but just for minutes to hours. And that is sufficient for some academic experiments, even for some perhaps space applications, but not if you want to run this at industrial scale and to cool a quantum setup. Notably, if your quantum setup loses all information or calibration once you warm it up. So if you want to make magnetic cooling useful for these applications, you need to implement it in a continuous fashion. And that is precisely what we did at kiutra. And even before we founded kiutra, what we developed at TUM and then span out. So we're the first and so far still only company in the world to offer CADR, continuous adiabatic demagnetization refrigeration, as a commercial product. And the way you can imagine how this works is that you no longer are working with just a single magnetic cooling unit per device, but actually we have always at least two of them. And they're connected and they're very carefully balanced such that one can provide the cooling to the payload while the other one is already regenerated, so magnetized again, and then cool down to the target temperature so that it can take over the cooling of the payload once the other unit has become depleted. And it sounds like a very trivial approach, right? And you see this in many other technical applications, but the technical implementation is not so straightforward. And that is why it took us many years to develop that. And this is also where we build a lot of experience, know-how, and even IP to build products that actually can do this reliably, repeatedly, leveraging magnetic cooling, not in a one-shot, but even continuous manner.
Is it fair to say, if I compare it with the semiconductor world, that's like ASML, like a wafer handling, then you have the next wafer, the next electromagnetic cooling, and
yes,
or with ASM International, that you have multiple chambers.
So in fact, what we have is like a single chamber. So there's one device, but within the device, we're running multiple cooling units, and they work together to act like a magnetic heat pump to generate continuous cooling. And this will eventually allow to apply this technology to a broader range of what it has been used for in the past, and eventually use it for the very same applications that have only been accessible through dilution cooling in the past.
And Alexander, when was this technology working? Is it very recent, or do you have it already a while, or was it prototyping, or what is in your roadmap on the progress there?
So the technology is working. It has been validated in the market. So we built the first proof of concept even before we spun out kiutra. So that was back in, I think, 2015, 16, 17. We secured first grants, academic research grants, to build the first proof of concepts. We built several prototypes, and then already our first commercial product, so the first deployment we ever did back in 2019, provided that continuous cooling technology for our first customer. And since then, we have, of course, massively improved the performance of this technology. So we have improved each individual component that is needed to run such a system. So the core components are, of course, the magnets, the cooling media, the thermal switches. There are many components that are actually required to build such a machine. And we have, of course, improved all of them throughout the years. So I remember that our first proof of concept device required 4 magnetic cooling units housed by one vessel, so 4 magnetic refrigerators, to provide cooling down to about 500 millikelvin with very low performance. So nowadays we can cool continuously to as low as 100 millikelvin using only 2 magnetic cooling units, and we're getting higher performance, higher power just with the 2 units that we're using today, thanks to this ongoing effort and development in the components, including also the software control, the algorithms that we're using to build those machines. Wow. So that is available since a couple of years, and it's validated, of course, in the market. So we have multiple machines out there that are using this principle.
Okay, that's clear. And then you claim to be helium-3 free cryogenic architecture.
Yes.
And that is because you work with magnetic. Is that correct?
Yes. So if you look into the cooling chain of a millikelvin machine, a millikelvin cryostat, so a modern commercial off-the-shelf device, then there are 2 technologies involved in any device. First is the pre-cooling that spans typically room temperature to about 4, perhaps 3 Kelvin. So to about the boiling temperature of helium-4, the the predominant helium isotope on Earth. So this is the pre-cooling. But then to get to even lower temperatures, so to the sub-Kelvin or millikelvin temperature range, you need to add another cooling principle. And in dilution cooling, that is the helium-3 dilution refrigeration, right? So you're starting at about 3 Kelvin with your pre-cooling unit, and then using helium-3 based dilution refrigeration, that second part will get you down or get your payload down to the very low millikelvin temperatures. And so dilution refrigerators inevitably rely on the helium-3. That is where the whole cooling happens for the millikelvin temperatures. You cannot engineer around that. It is just a key requirement, and any dilution refrigerator, no matter how you build it and who builds it, will therefore rely on helium-3. And the more power you want and the more systems you want to deploy, the more helium-3 it will take. Now, our approach avoids that entirely. So we're also using for the pre-cooling part commercial off-the-shelf cryocoolers, typically pulse tubes cryocoolers, because they're silent. They don't introduce a lot of vibration, and they run a very long time before they have to be serviced. And that again brings us down to about 3 Kelvin. And then from the 3 Kelvin to get to the millikelvin, we're no longer using helium-3. But there we're applying our ADR or CADR technology to get the payload down to the millikelvin temperature regime. So we're essentially replacing that lower part of the cooling chain, which is by far more technically complex and also therefore more expensive, by our magnetic cooling technology.
Okay, that's clear. Thank you for explaining this. For the input and the output cables, do you develop them yourself, or do you work with external suppliers, or does it also matter if you use a helium-based architecture or a magnetic-based architecture?
So we're not building at the moment our own wiring. We're sourcing that from various suppliers according to our customer requirements. So we're essentially integrating whatever our customers ask us to integrate, and we're delivering turnkey solutions that work immediately after the installation. That typically takes a day or two. And we're sourcing therefore wiring from various suppliers. Some customers require semi-rigid, some flex wiring, and we're integrating it all. And we're integrating, of course, far more than just the wiring. We're integrating also low temperature, low noise electronics like amplifiers. We're configuring according to the customer requirements, the attenuation on each line. So we're in principle acting as a system integrator that builds out the cooling system such that it perfectly matches the requirement of the end user. That does not mean that we're building custom machines. So we have fully standardized products. Every L-type rapid cryostat is just another L-type rapid cryostat, but you can choose from various configurations, both in terms of the cooling performance it delivers and in terms of the wiring, integrated wiring and electronic setups, where we allow our customers just to pick from various options. So depending on whether you're, for instance, a superconducting qubit user, you want typically magnetic shielding in your fridge, you want a different line setup compared to, say, a spin qubit user who want a superconducting magnet in the fridge, not magnetic shielding, but a superconducting magnet. And of course, again, a different wiring configuration and different electronics. And we offer all that so customers can just pick from various configurations and options.
And to recap, there are two disadvantages of helium-3. The first disadvantage is okay, you're dependent on other countries. You're dependent on the US. Or maybe Russia. I don't know if Russia also has that.
These are the two major producing countries, but of course Russian gas is no longer available to the Western world after the invasion of Ukraine. So the major supplier of commercial helium-3 these days is the US or North America, who get the helium-3 mostly from military stockpiles. There's a single civilian source, to the best of my knowledge, in Canada, Ontario, Canada. That is a special reactor source that has been optimized to harvest the helium-3 that is generated in that reactor. It's a special type of nuclear reactor, and that can then be sold off, so used for commercial applications. To the best of my knowledge, that's in fact the only civilian source of helium-3 today.
And that's so part of it is geopolitical. Then you're dependent on other countries. and especially for if you have computing is intelligence, and so that's you want to be sovereign, you don't want to be dependent. But
Yep.
also you mentioned if the volume scale, there's not enough supply. Can
Yes,
you quantify
that?
that?
Yes, of course, because so even the US, I think, have realized that if quantum is to become a mature industry and quantum computing is to be deployed at scale, there will also in the US not be enough helium-3 to operate the cold infrastructure to run those machines. So if you look into the roadmaps, and I think the best known roadmap is probably the one by IBM, you see that they are mentioning for the larger fault-tolerant quantum compute setups that they are planning, they need massive cooling power. And if you translate this into helium-3 demand, it turns out that such large-scale installations could require a substantial fraction of the global annual helium-3 supply, meaning that you could probably deploy 1, 2, 3, perhaps 5 systems a year, and then all the global helium-3 supply per year would already be consumed for such machines. And of course, that's a no-go. I think nobody wants to spend billions in the development and then commercial rollout of quantum computing if we only can deploy 3 systems a year. I think that's not the idea. And that is why we need an alternative. Yeah.
But apart from helium-3, let's say there would be enough supply, which your point is, it's not. If there would be enough supply, then how does your standalone, how does your cryogenic cooling architecture, how does it compare to helium-3 based architecture? Are they standalone also better or equal or?
Yeah, I would say it's still better suited. That's the point I want to make here. So, and the reason for that is that dilution cooling is a perfect technology if you want to generate a lot of cooling power at the very low millikelvin temperature. That is very nice, but actually that's not the only thermal stage where you need cooling power in a real-world quantum setup. So you also need cooling power at intermediate temperature stages to cool and pre-cool electronics that, in contrast to the superconducting QPU, generate excess heat, and the wiring setup, for instance. And that is fairly hard to achieve just by multiplying multiple dilution refrigerators and interconnecting them. So what you end up with is actually a very large dilution refrigerator setup that first costs a fortune, second eats a lot of space in your facility, and then over-delivers cooling performance in certain temperature areas just to reach the relevant required cooling performance at other slightly higher, in fact, thermal stages. And this can be overcome also by switching to our alternative cooling technology, where we can engineer cooling modules to provide the cooling power and the base temperature exactly tailored to really the requirement of the end user application, which is very much different. For instance, if you compare superconducting quantum computers with spin qubit setups, just to give one example. And then that's also the reason why we are talking here no longer about just a cryostat, but we really say it's a different architecture. For the first time ever with the X-type, we're introducing a spatial separation of the cooling, so the cooling infrastructure itself and the payload, the quantum setup. What that means, you can actually deploy and scale the cooling independent of your quantum setup, and you don't have to start all over again once you move from one chip generation to the next one.
And
because
Alexander, what do you mean with that? You said you can deploy. I don't fully understand what you mean with that. Could you quantify it?
If you look, so if you look how a quantum computer looks today, just do the Google image search again, and you see there is, of course, this nice dilution refrigerator, and integrated, and I think that is the important point, integrated with your dilution refrigerator, you find the wiring and your quantum chip. So it is an integrated setup, and it means that a chip or a quantum computing manufacturer needs to buy the dilution refrigerator. It is then shipped to the chip manufacturer, and they do the system integration. So they really integrate the wiring, the electronics, the chip into this large setup, and then they test it and send it to their end user. And this is a huge effort because the machine is super large. You need a jumbo jet to fly to the end user. You may have to tear down a wall to get it into the facility eventually. So that is not so straightforward. And the problem is the setups get ever larger. So we're not stopping here. So there's a clear tendency to larger setups where you're even interlinking multiple quantum chips to get an overall higher performing, high fidelity quantum computing setup. So, and therefore, and I think this is where we are now following a completely different approach, and we call it an architecture. Therefore, for the first time, we're really now separating the cooling. So we have modules. So we have parts of the whole setup that exclusively house the cooling, our magnetocaloric refrigerators, and they are spatially separated from another module or multiple other modules that exclusively house the quantum payload. And that is very nice because the quantum computer manufacturer can eventually focus only on integrating their quantum payload in their own housing, and they can even ship and deploy it separately from the infrastructure that we can set up and the end user facility in the meantime. They can also have their own testing cooling infrastructure once in their facility, and as they're building more than hopefully one quantum computer, they can connect one payload, test it, improve it, and eventually deploy it, and then on the same cooling infrastructure run the next test. So you're not replicating the whole cooling for every system that you're deploying, but you really can rely on a spatially separated remote cooling infrastructure. And I think that is the way to move forward, also because it is far more future-proof. Just think of this clear tendency of building ever larger setups. If you want to do that with an integrated setup, you have to buy an all-new fridge every time and start all over again, while with a highly modularized, spatially separated cooling infrastructure, you can just add further cooling modules. As you don't throw away what you have already, you can expand your existing setups. So this is far more sustainable, far more cost effective, and it can grow along the roadmaps of the chip manufacturers.
I really like the modular approach. I think that's very helpful. But I want to clarify something. So you also mentioned that for cooling down to the extreme cold millikelvin temperatures, helium-3 is required. But can you do you then have a hybrid approach that you say, okay, in certain stages we can do it with magnetic cooling, but for the most extreme cold scenarios we use helium, but we use much less because we maybe 80% of the process of cooling we do with magnets, but only the last 20 or 5 or 10, I don't know what percent, there we need the helium-3. Is that fair to say?
You could do that. I think it's a valid approach, but the question is, why would you want to do it if you could cover the whole temperature range exclusively using magnetocaloric?
Okay, perfect. So just to clarify, you use 0 helium-3.
Yes, exactly. Along the whole temperature range, essentially. And we can get to the very same millikelvin temperatures. So the X type that we have now announced will cool down to 20 millikelvin with a comparable cooling power even in the base setup to what a larger modern dilution refrigerator can already deliver. And it has the clear advantage that if you need more space and more power, you can just add as many modules as you want to get ever more space and more cold. And then you can also add modules that get you additional cooling power, not only at millikelvin, but actually at interim temperatures, thermal stages. And that is then altogether far more effective compared to a single dilution refrigerator approach that suffers from the lack of these engineering of the target temperature and cooling power to the respective intermediate temperatures.
Okay, that's clear. Thank you for clarifying. But what's still not clear, what's open for me is that, so you said, okay, we can do 20 millikelvin temperature, but can you also go to 200 millikelvin? 200?
Yes, we can. Yeah,
okay, so that's not an issue.
Yeah, and what is so great is that at 200 millikelvin, of course, we have, using the same footprint, the same energy consumption, we would have even far more cooling power. So it is by far easier to get to these higher temperatures. What we're currently working on, and that is what we're delivering with the X-type, is the very low temperatures. So our commercial systems currently specify a minimum temperature of 55 millikelvin, which is perfectly fine for the testing, characterization, and qualification applications. But it's not sufficient if you wanted to run a large fault-tolerant full-stack quantum computer. And that is why we're bringing this down to 20 millikelvin, and we have demonstrated already here in the lab. So we have our low temperature record is down to I think 10 millikelvin already. But of course, we want to operate at around 20 millikelvin with a reasonably high cooling power. And that is what we're currently building as the first demonstrator. That should be finished by end of the year. And we're now engaging with beta partners through our beta partner program to lock in the first testers and commercial deployments that we're anticipating for the next year.
Wow. Okay. You clarified that. But then if we're going to scale, so how much space, one question before we talk about the scaling, how much energy does it consume?
Yeah, so it does not consume more energy, even a bit less compared to dilution refrigerators. And the reason for that is that the dominant factor that drives the energy bill in all cryogenic equipment nowadays is not the millikelvin cooling part of the cold chain, but actually the pre-cooling. And that is the same for both dilution refrigerators and our ADR or CADR technology. It's the closed cycle cryocoolers that provide the cooling at about 4 Kelvin. And it takes about, depending of course on the specific device and manufacturers, it takes about 6.5 to 7 kilowatt electrical input power to get you 1 watt of cooling power at about 4 Kelvin. So ballpark, you see that it actually takes a lot of energy. However, if you compare that to, say, nowadays AI setups, it is negligible. So I think some years ago, everybody was afraid that cryogenic would cost so much energy to eventually run a quantum computing setup. I think comparing this now to what AI takes in terms of input energy and cooling, it is completely irrelevant. So you can easily get that energy in any data center, in most even user facilities.
Yeah, they say when I spoke to Olivier Ezrati, he disagreed a little bit on that. So my view was the same as yours. I said, look, in AI they have gigawatts. And you're talking about watts, so why bother? And then he said, Frank, the difference is, for AI, it's used by hundred thousands or million users. And for quantum, typically there will be one user per use case, or a few. So then we need to divide the energy budget by one user, and then the cost can still be high, relatively speaking. But then the question is,
I agree to some extent, not completely, but because, of course, first, I think quantum computing setups will also be shared amongst different users, which is already the case if you're buying compute time from some of the commercial providers that are already offering that, quantum as a service. And then I think we should also consider that by introducing cryogenic cooling and quantum computing as a new compute paradigm, that, of course, offers the great chance of lowering the energy bill for AI and any other HPC compute, right? So I think it would allow for the first time to address very, very complex problems. If you want, you couldn't even run them or solve them by means of classical computing, classical high-performance computing. But if you tried, or if you are getting even close to the complexity level, I think the energy consumption would be far larger than anything that could be achieved by means of quantum computing, even if we take into account the power consumption of cryogenics in there, in the total bill.
If we then talk about scaling quantum computing, let's call it superconducting quantum computing, how can you scale the amount of qubits, and what a bottleneck is the cryostat? So you said already, okay, there are some shutdowns, and so the automatization of that helps. And you said, okay, kiutra has 3 to 8 times the throughput of competitors, and that's helping. But if you think about how much energy budget or heat budget is there, so when I spoke with Saul Bosman from Delft Circuit, ex-CEO, then he said they used analog cables, lithium, natrium, flex cables, because they said, okay, if we would, I was asking him, why are you not using optical? And then he said, well, Frank, an optical cable, just putting the laser on might blow up already the cryostat. I don't know if that's true or if it's only based on helium-3, but he said that would consume too much energy usage. And that would, but how does that work? Could you explain those bottlenecks, and then what is on your technical roadmap to expand that? And then in the end, will we, so now in semiconductors, we have a cooling room, we have clean rooms. Do you think we move to cooling rooms? So that we get one big room, which is a total refrigerator?
I think, yes, that might be the case at some point. But honestly, so just looking into HPC or modern data centers, you also have a pre-installed cooling facility there, right? So once you install a new compute rack, you can connect it to some cooling that has been established by the data center provider. And I can imagine that down the line, we can also see something similar happening for quantum computing, where data centers are also offering a dedicated quantum cooling infrastructure, allowing various quantum computers and modalities to just be plugged in, and then, cater compute time to the data center users. So I think that is actually, for me, seems to be quite natural development as the whole technology stack becomes more mature and as we see more deployments, because it's simply driven by financial aspects. So I think it's cheaper, more sustainable, and you want to build a cooling infrastructure that can be used not by one but by multiple modalities and can be installed independent of the individual quantum computers down the line. Of course, we're of many years away from that, but I would actually expect this to happen at some point. Now, how I see the industry scale up, looking into superconducting quantum computers specifically, you mentioned this bottleneck in testing and characterization. I think it exists, but I think what is even more important is how to scale the setups that are then eventually deployed. So in the operation phase of the product, not in the R&D and qualification phase, but really in the deployed and operation phase. And I think there's a tendency, there's a trend to, of course, build better processors that implement also error correction. And I think one way forward is to then use multiple quantum processing units that are working together to eventually build the final quantum computer that has the great advantage that you can get very high fidelity for each individual quantum processor without a need to build one ever larger chip. So it's very positive from a fabrication perspective, quality perspective.
Alexander, just a clarification question. Do you mean, what exactly do you mean? Do you mean on one chip, two QPUs are connected and both are put in one cryostat?
Yes.
Or do you say you link two independent cryostats, so one chip in one cryostat and one chip in another cryostat, and you link the two?
I mean, it's essentially the same. It's just a matter of the distance you have between the two chips, right? If you make it very close, then from the outside, it will look like a single cryostat and a single chip. But I think if you have a means to coherently connect at low temperature, of course, I think that's a requirement, two chips that are even distant. And of course, keeping in mind that it requires some bandwidth and reliability here, that would also allow to get some spatial separation between individual processing units.
And is your belief that the control electronics, should they eventually also have to be in the cryostat, or can they be kept out?
Yeah. I think they are, to a great part. They are already in there, and I think it's natural to move them closer to the processor because, of course, it's easier if they are already operated at low temperature in terms of thermal noise that they're introducing to the QPU. So the closer you get them, the colder you get them, the easier to interface them with your quantum setup. But of course, that also has to be taken into account when calculating the heat budget. And of course, there is continuous improvement on that part too. So I think those devices...
Can you walk us? Yeah. Can you walk for the listeners who are not familiar with the heat budget? Could you explain the basics? What is the heat budget and why does it matter for cryogenic cooling?
Yeah, so in order to operate the QPU, the quantum processing unit, it just needs to be very cold. And when I say cold, I mean about 15 to 20 millikelvin. So that is extremely cold. It's far colder than outer space. So space is background radiation in space is 2.7 Kelvin. So that is in a quantum computer that is much colder than that. And the reason for that is not that the chip would generate heat by its operation, like in a traditional processor. But the reason for that is that only at those very low temperatures, the quantum mechanical effects are stable enough to be exploited for the quantum computation, so to speak. Right? Now, the problem is to do a practical calculation, to do something meaningful with a quantum computer. It takes a lot of quantum bits, qubits, and they also have to be wired. So you have to read them out, you have to configure them, to manipulate them, and to do so you need to wire them, right? And that is like in any classical processor, you have a chip and you have a fan out, and then the chip is wired. And of course now those wires, they are connected eventually to electronics that sit at room temperature. And heat is running through those lines into your setup and will eventually reach your quantum processor. And you have to take really great care to avoid all parasitic heating, all excess heating running through those lines. That is why, for instance, Delft Circuits is developing very thin superconducting flex wire that is lowering substantially the heat that is introduced from room temperature down to millikelvin temperatures through those lines. And in order then to keep your whole setup, including the chip, but even more importantly than all the non-superconducting components that are used to read out and control the chip cold, you have, of course, not infinite, but very limited cooling power provided through your refrigerator, be it your dilution refrigerator or in our case, our magnetic refrigerator. And this limited cooling power, that is what we call the cooling budget or the heat budget. So once you introduce more heat through your lines, through the operation of your quantum computer, then your cooling setup can deal with, your chip will warm up and everything breaks. So you can no longer use it. And so just to give you an ballpark order of magnitude, typically we're talking about microwatt to perhaps milliwatt of cooling power at these extremely low temperatures. So this is very, very, very small compared to what you see in other industries where you have, for industrial applications close to room temperature, kilowatt or more of cooling power. So here we're talking about really, really tiny powers. So you have to be extremely careful about your budget and spend a lot of effort in optimizing not only your chip, but also all your integrated electronics, the wiring tree, and anything that adds to your budget.
And how can you increase the budget? So if we now go to the roadmap of kiutra, the space inside the cryostat and the heat budget, the coming 5 years.
Yeah.
What is on your roadmap? How much will that change, and how does it enable the quantum computing companies to grow?
So just again to give you a number here, today we're with our qualification systems, we're delivering order of magnitude 1 microwatt at these very low temperatures. 1. Not exactly, but order of magnitude. Now with the X-type, we're going to order of magnitude 10. So a base system will already deliver 20 microwatt at 20 millikelvin. But the idea is that in principle, you can get any arbitrary cooling power just by adding more modules. So you can easily go to hundreds of microwatt and of course down the line also milliwatt of cooling power at those very low temperatures, say 20 millikelvin, simply by replicating always the same cooling module that houses our magnetocaloric refrigerator. And in principle, that follows the same design idea that you are already seeing in dilution refrigeration. So I think they're doing the same since many years. So of course there are small dilution refrigerators that deliver little power, and then you can build them larger to deliver more power. That's straightforward. It means that you're circulating more helium-3 to get more power. And then you can multiply and interconnect various dilution refrigerators and make them one connected cooling device. And that is also what is already done in the industry. simply to get more space, more cold space, and more power at these very low temperatures. And I think that is clearly where most of our competitors are also moving toward. If you happen to be around at the last APS Global Physics Summit, I think most of the dilution refrigerator manufacturers, Blueforce, Mabel, ICE Oxfords, you name them, have introduced or announced at least setups that are combining in a modular way, but in a different modular way than what we talk about when we say modular design, larger setups that are just interconnecting more dilution refrigerators to provide the cooling power that will be needed down the line for those large fault-tolerant quantum computers.
Okay, thank you. Maybe I've got two more questions. The first question is, okay, helium-3, that has some geopolitical consequences. Magnets typically are based on rare earth materials.
True.
Are those rare earth materials in Europe? And can
Not
they
yet,
be
of
mined
course.
and processed?
Yeah. So in principle they could, but realistically, if you look into the supply chain, what we have done very thoroughly, you notice that of course those magnets, as you say, rely on rare earth that typically are sourced not from Europe, but from China or Brazil. Just to get you some context here, when we say magnets, we're not at all talking about the normal magnets, the permanent magnets. In our case, we're exclusively talking about superconducting electromagnets, and the material used to wind those coils is niobium titanium. So it's about the niobium and titanium here. But first, niobium titanium in such a wire makes just a very, very tiny fraction. The greatest part of the wire is copper. And second, in principle, that is an established and very large diversified supply chain, because it's a standard wire that has been heavily used in many other applications, from generators to medtech. Think of NMR machines, where this is also, of course, used. But we're looking into this very carefully, and what we therefore also propose, and I think that is has to be applied not only for magnets, but for many other materials in the stack, in the value chain, is also a more circular approach. Because of course all these materials, they last forever and they could be recycled if we wanted to. There is a lot of those materials even within Europe, and there are companies starting to build processes that would allow to recycle them to increase the resilience and supply chain resilience for companies and customers in Europe. In fact, that is something that we're presenting, also an idea we're presenting just now at the Q Expo in Spain, where Tomek is taking part. And this is something that we're introducing together with Circular Republic.
Okay, well, thank you for explaining. Maybe to wrap it up, for investors, why should they look at to conclude why is kiutra an interesting company to invest in or to research?
Yeah, so I think it's interesting because we're actually building the cooling infrastructure that will be crucial to make quantum technologies, notably cryogenic quantum computing, an industrial mature technology. It won't go without that. And I think it's a perfect timing to look into this right now. And this is also what makes me very excited about this moment. I think we are now seeing a very unique and cool combination of two factors that we have been working toward for quite some time. First is, I think, external recognition. And second is our internal technology readiness. So by external recognition, I mean, we went out back in 2018 telling people, look, you're building quantum technology on sand, so to speak. It is not a solid concrete that you're building upon. You're leveraging a technology that has been around for decades, but mostly for academic purposes. And it's not an industrial technology, and it's also vulnerable. So it has a very unclear supply chain. And so we started with that very early on, and it's great to see that it's now being recognized also by the market. So there's independent research to this topic. There has been just a few weeks ago a very nice article published by the Science magazine. So I can highly recommend this. It's a nice read for anybody who wants to dive deeper into the topic about helium-3 supply. Beginning of the year, DARPA has issued a official request for information seeking specifically cooling technology that can provide sub-Kelvin cooling independent of helium-3, again showing that this has been recognized as a potential choke point. So I think the market is now coming to the same analysis that we started from some years ago. That's the first thing. And I think the second factor is technology readiness. We have built this new cooling technology from first principles, and we have throughout the last couple of years already validated it successfully in the market. We're now building the larger scale system, the X type, and it will be completed as a first demonstrator already this year. And then I think we will be able to offer the same performance power, just like that so far has only been accessible. There has been no alternative. It only has been accessible so far by means of dilution refrigeration. And I think that's exactly that very cool combination that we are facing right now, and that makes me at least very excited about the potential of kiutra and our next steps.